Hello, fellow problem solvers. So today we're going to be doing an algebra problem, namely, let a, b, c be real numbers such that a times b is not equal to 0. Prove that these two quadratic equations share a solution if and only if a cubed plus b cubed plus c cubed is 3 times a times b times c. I invite you to pause and try this problem out for a minimum of 15 minutes, ideally 40 minutes to an hour, not more than an hour and a half really. If on the other hand you'd like to go along with us, pause and think for 10 minutes and see what your next steps would be. And now, without further ado, let's begin. So for me, what I'm seeing here is two things. There's some background knowledge I have that I'm going to be using for this problem. And I think that's where I want to begin. The first of things like this condition right here. What does it mean? So this condition here, I know an identity, which is that a cubed plus b cubed plus c cubed minus 3abc equals to 0, but I know that I can factor this. And here's how I can factor this. If you're looking at, I'm trying to find a motivation for the factoring, and the only motivation I'm coming with is that, mind you, this is equal to 0 when? If you look at this as a polynomial in some x, right? X cubed, x times b times c, right? When is this equal to 0? For what types of x? Assuming you don't know anything about b and c. And the answer here is, and sort of to motivate this is going to be difficult, but here's one way. Here's a minus sign. And this is 3 times b times c. X will need, if it's 0, it needs to be something that has b and c in it, some relationship with b and c. If it's and it also has to be of, what's it called? It needs to be of the power of x, like it needs to be a linear combination of b and c plus some constant. It can't be a quadratic. If you had like b squared in it or b times c, then this thing right here would not be canceled. It would be very hard to cancel. Say if it's b times c, then you have b cubed, c cubed here. And here you would have a power of 1 to 4, right? You'd need sort of a linear combination of b and c. So it's going to be some b lambda plus c gamma plus some delta, right? That's what this x is going to need to be if this is factorable, if it has 0. So, but you can also look at it, wait, b gamma, b lambda, c gamma. Let me try to see like what happens when I just have like b plus c. And when you have b plus c, the trouble is like these don't cancel out. So for them to cancel out, because you're going to have a b cubed here, and mind you also see like you need to have b and c need to be alone. They can't have anything. So this is b plus c plus some delta. Why do they need to be alone? They need to be alone because only the cube outside of that will cancel out with b cubed. You won't have sort of b cubed and c cubed separate here. So we'll have some b plus c plus some d. But it can't just be some b plus c, it needs to be negative, right? It needs to be negative because we need to cancel the b cubed and the c cubed. And if you see like, wait, when you plug negative b plus c, you'll have negative b cubed plus c cubed plus 3bcb plus c. And that's what you get here as well. So you know that a solution to this is x is equal to negative minus b minus c, which means what? Which means you can factor this as, like this is a solution, so you can factor it as like minus this, like x minus this. Or for our a, that means that we can factor this as a plus b plus c times something else. Now, what is that something else going to be? Well, we need a cubed, so put in a cubed. But then what do we get? We get a squared b. We need to get rid of a squared b. How do we get rid of a squared b? Well, we need to add a minus ab. We also need to add a minus ac. And similarly, we also need to add a b squared, a c squared, and a minus bc. And what happens is once you actually put all of these in together, you're going to get minus AB, minus ABC, minus ABC, you'll get minus 3ABC. So you will get that this thing right here is actually equal to this. And so with this sort of factoring, you have the condition is that this is equal to 0. When is this equal to 0? Either when a plus b plus c is 0, or when this is 0. When is this 0? Well, this is a half times a minus b squared plus b minus c squared plus c minus a squared, right? So this is equal to 0 when a is equal to b is equal to c. It's immediate for me why that will give us here that we have a shared root, because then you'll have ax plus c on both sides. They'll have a shared root. They'll have both shared roots. And in this condition, I'm not really sure when this is 0, why exactly this happens to have a shared solution. Like, that's a bit of a mystery to me. But that's going from this side, from this side to this side, using some background knowledge. And now with this sort of background knowledge, I invite you to pause for another 5-10 minutes and see if you can push the problem further, because here for me is the next step. Okay, so this is what I have when I divide by this. And now when I think about, okay, let's see what happens when they have the same solution. So say this one is x1, x2, and this one's x1, x3. What happens when they share a solution? Well, we can write this as x minus x1, x minus x2 is equal to this. What does it give us? It gives us x1 times x2 is what? It's equal to c over a. x1 plus x2 is equal to what? Minus b over a. Okay, and then we have x1, x3 is equal to a over b. And we have x1 plus x3 is equal to negative c over b. And now, what's sort of interesting to me here is, first of all, like these two sum up to 0. And like there's some sort of, I'm not sure yet just how we're going to get that a plus b plus c needs to be 0, or a, b, and c need to be equal all to each other when we have this thing. And here's where I invite you to pause for another 5 to 10 minutes and see if you can push the problem further. Push it maybe from this direction. Or actually, push the problem further. Like, what happens if a plus b plus c is 0? Why would this be true? Why would we have the same solution here? Pause now. And here's the next step. So, if c is minus a minus b, then we have in the first equation, x1 and 2 is minus b plus and minus the square root of b squared plus 4a times a plus b over 2a. And it seems like, wait, we have over 2a over 2b. How are we ever going to get equality? But the thing is, first of all, this is b squared plus 4ab plus 4a squared, which is b plus 2a squared. So you can get rid of the square root, and you have this will be minus b plus and minus what's going to be b plus 2a over 2a. And then this thing right here will be equal to what? A plus b plus and minus, this is a plus b squared minus 4ab is a minus b squared. So this is plus and minus a minus b, all this thing over 2b. And I got worried for a second, did I make my calculations wrong? Were my calculations wrong? And the answer is no. And here's why. When you get when you have the plus, you'll have b's will cancel out, and 2a over 2a will cancel out, and you'll get 1. And here as well, you will also get 1 as a solution. And with that, you will have, if c is minus a minus b, then they share a solution. If, on the other hand, a is equal to b is equal to c, then they obviously share a solution. And now with this, we know that, given this is if and only if, like if this is true, then this is true, but then also this is true back again. So we know that if these two share a root, this solution, will either have the case when a is equal to b is equal to c, in which case that root is going to be something. What is that? Then that's equal to solving x squared plus x plus 1. Though that actually, to be fair, x squared plus x plus 1 is x plus a half plus squared plus 3/4, which doesn't have real solutions. So that case just falls off the ground. So if these two share a real root, share a solution, then that root will have to be 1. And more to the point, the other roots, one will be What's this going to be? This is going to be minus, so when we have a minus here, then we're going to have anything nice? No, I don't think we have anything nice. Here we have minus b plus a over a. And here we will have a over b as the other root. So there's not much we can do with the two roots. Well, that's not actually true. I mean, this root plus, it's just, there's nothing else nice to it, but we know that the other root is 1. So now with that, let's take the case when these two share a solution. What will we do then? And this is something that took me a while to figure out, and I invite you here to pause for 20 minutes and see if you can figure out what would you do if these two share a solution, a real solution. What would you then do with this sort of equation? Pause now, and here is the next step. So, just to make things clear, I've said, like, let S be this same solution that they have. Now, that means when we plug in S, these two things are true, right? Why do I do it like this? Well, now, let me see can I figure out what S is from here? And the answer is yeah. I want to show that S is 1, right? Because when S is 1, I will have that 1 plus, so this is going to be A over A plus B over A plus C over A is 0, i.e. A plus B plus C is 0, which is what I need to prove. So now can I find S? And the answer is yes. Can I find S? Yes. It rhymes. That was not planned. Now, so what will I do to find S? Pause for a minute. What would you do to find S? I'd subtract. Subtract, then you get rid of the S squares. I hope. Like if you wanted to say do the quadratic, this is the solution you would get the quadratic from here. It wouldn't be very nice case by case analysis. I don't want that. That's just too much work for me. So let me subtract. Shortcut. Subtracting, we get S times, so this is going to be over A minus C over B is going to be equal to this minus this. Let's move it on the other side immediately so that it's this minus this. And this is going to be A over B minus C over A. I don't think I've made any mistakes here. B squared, A squared, no, it's all good. So what does this give us? Well, this gives us that S times B squared minus AC is equal to A squared minus BC, right? So, and why does this give us this? Well, it's just, how do I put this? I mean, I just like multiplied everything by A and B. That's one way of putting it. And now this gives us that S is going to be equal to A squared minus BC. So that's what we get here, over B squared minus AC. A squared minus BC over B squared minus AC. And now, this S makes both of these 0. So now with this, what would you do? I invite you to pause for another 10 minutes and figure out what your next step would be. And here's the next step for me. So we use Vieta's rules. Instead of we have S, we can sort of plug it back into the original, but plugging it into the original gives us a degree 5 polynomial, which is just more difficult to factor. You can try, put in the comments below. I went down that route. It's a fair route to go down, but I found myself, I do not want to see what this polynomial is equal to. No, just no. So let's look at Vieta's rules. And what do we have from the first rule? So we have S times x2, where x2 is the second solution here, will be equal to what? It will be equal to C over A, and then S plus x2 will be equal to B over A, like negative B over A. So now plugging this in, we have that the first solution, the first thing right here gives us that x2 is going to be equal to 1 over S, C over A, which is going to be equal to B squared minus AC times C over B squared, so over A squared minus BC over A. Now this gives us S2. And now let's do the same thing here. We will have, on the other hand, we'll have S plus x2 is equal to negative B over A. So S2 is equal to negative B over A. And it's minus S, so this is plus a squared minus bc, b squared minus ac, which becomes negative, what is this going to be? We're going to have a cubed plus b cubed minus 2abc, and everything over a times b squared minus ac. And now this is the same x2, so these two expressions must be equal. The only nice thing about them is that the a's cancel out. And you might say, wait, this is still a degree 5 polynomial on both sides. Yes, it is, but it factors out nicely. Namely, if we factor it out here, and we get this thing right here, and then once you multiply everything through, and here's the thing, there's not a lot of things to multiply through. What do we get? We get here b to the power of 4c minus 2b squared ac minus 2ab squared c squared, because the c multiply, and then we get plus a to the power of 2c cubed. And on the other hand, we get bca cubed, and what do we get? We get plus b to the power of 4c, we get minus 2ab squared c squared, then we get minus a to the 5th, we get minus a to the power of 2b cubed, and we get plus 2a cubed bc. And now what happens here? What cancels out? Well, this thing right here cancels out with this thing right here. B to the power of 4c. Actually, we have multiplied this incorrectly. This is b. So it's so this is bc times b cubed, right? Oh no, this has actually been good. Wait a second, what have I done? This is bc times a, so it's bca cubed. bca cubed. And now b to the power of 4c and b to the power of 4c cancel out. And what we're left with when we move everything to the other side, mind you, we also have that these two things add up, and they add up very, very nicely. In fact, let's move everything on to this side. And also we can then divide everything by, we'll just grab a squared outside and we'll get a squared. We get c cubed. When we add these two together and get a squared out, we get negative 3abc. Take a squared out here, we get plus a to the power of 3. Take a squared out here, we get plus b to the power of 3. All of this is 0. In other words, we have proved that if this is the case, then given a isn't equal to 0, we know that a cubed plus b cubed plus c cubed minus 3abc is equal to 0. And this finishes up going from this side to this side. We've already went from this side to this side. Really, we just said like there's these two cases. That, like this implies either a plus b plus c is 0, or a is equal to b is equal to c. If a is equal to b equal to c, like they share the same root. But actually, it doesn't matter if it's real or not. They share it. We're done. If a plus b plus c is 0, we've also showed that this shared root is going to be 1. Unfortunately, here we haven't really proved that s is equal to 1. Like, it's not the thing we use to get to our proof. Namely, we just did a lot of calculations, but smart calculations using Vieta's rules instead of just plugging everything in and trying to check it through, which I think is a lot more difficult, or at least a lot more time consuming. This finishes up our lovely little problem, and it's a heavier algebra problem, and I wanted to show it to you. I thought it was a lot easier actually before I did this, but then I saw, okay, let's just like do a problem like this. So this finishes up our proof, and as always, thanks for problem solving.